All right, Ramesh, it's about that time. Shall we get started?
Yeah, let's go for it, Arun.
Awesome. Hey, good afternoon, everybody. My name is Arun Thuraviyam. I'm a product manager here at Go Engineer, and I'm here with a special guest today.
Hey guys, welcome everyone, and thanks for joining us today. So my name is Ramesh Lakshmipathy. I'm actually with Dassault Systems SOLIDWORKS, and I'm actually one of the technical managers on the North American SOLIDWORKS simulation team. So we cover all the SOLIDWORKS simulation tools that you might be familiar with, and also the Simulia Abacus solutions on the 3DEXPERIENCE platform. Glad to be here, and thanks, Arun. Let's go for it.
Awesome, thank you. So I'm sure you guys understand what you signed up for. We are going to present the 3D Experience Simulation Suite, specifically focusing on the industrial equipment segment. So we're essentially going to go through the product portfolio available in 3D Experience and give you an idea about some of the challenges faced by industrial equipment area. We have a couple of product demonstrations lined up, and then we'll go into how this technology has been adopted by certain companies in the industrial equipment segment and how they're successfully using these tools for product design. And finally, we'll wrap up this presentation by summarizing the entire product portfolio, or the simulation portfolio, with the 3D Experience platform. Now, when you take the industrial equipment segment, right, this segment is essentially divided into about 6 areas, right from the industrial robots to manufacturing equipment, all the way to building equipment. But we've noticed that all of these companies or all of these areas essentially share one thing in common, is that they have a lot of moving parts that undergo structural loading. So what this involves is they're not only statically testing their components, but they're testing their components in dynamic and vibration environments. And one key area of interest for a lot of these companies is life cycle prediction. Not only do they want their components to survive for a single loading cycle, but they want their components to survive for multiple loading cycles and essentially ensure that they have good fatigue life. To that end, this industry tends to be one of the largest adopters of simulation, and they have a couple of processes on how they've implemented simulation, their product development process. A very common process is a serial process where there's one person developing the concept, and there's another person who's running the simulation. So there's a back and forth between two different design and analysis tools. As a group, they iterate through the design to achieve the final product. But with some of the tools that we have available in SolidWorks and Dassault Systemes, we essentially proposed an integrated engineering process, which is popular amongst our customer base, where the tools are so that you can essentially do the concept development and simulation simultaneously, because the tools are all integrated. So both in the conceptual phase and in the product design phase, you have access to these simulation tools that plug in, that enable you to do this and reduce the number of prototypes and achieve a mature design much faster. Well, whether you adopt a serial process or an integrated engineering process, the takeaway is that there are certain drivers that push these industries to essentially adopting the simulation technology, and one of the biggest drivers is market share. Essentially, it's a very competitive field, and a loss of about 0.01% of market share translates to around $12 million in revenue. Besides that, warranty claims is pretty common. Statistically speaking, about 1.5% of the products that are produced or sold are essentially returned as under warranty claims, and that constitutes about $2 billion in revenue. So it's a lot of money that to be saved by adopting these kind of measures to ensure that you have a good product that's able to function what it was intended for. There are other benefits besides just reacting to those drivers. One of the biggest benefits is obviously design validation, before product prototyping. Another one that these industries target is weight reduction. They want to use the least amount of material to be able to achieve the maximum performing product. And and this is a theme that we will keep referring to over and over again during the presentation, which is fatigue life. Focusing on how these components survive during the life cycle of use is a key aspect for this industry. Besides that, there are also benefits on the production end, because you're essentially reducing the product development time, and you're able to take advantage of that by increasing production capacity and product throughput. So these are some of the reasons why simulation is popular, and specifically why our simulation tools are very popular. So I'm going to focus we are going to focus today on the simulation portfolio from Dassault that's implemented on the 3DEXPERIENCE platform. So I'm pretty sure everyone on this call has heard of Simulia. Simulia is a portfolio of simulation tools from Dassault Systemes, and it's a multidisciplinary simulation suite. Essentially, you have access to finite element analysis technology, computational fluid dynamics technology, and electromagnetics technology. And we have one of the most popular and most widely adopted finite element analysis solvers out there called Abacus. Again, another name that's recognized by world over by folks in product design and analysis. Now, where the 3DEXPERIENCE platform comes in is these simulation tools from Dassault Simulia have been implemented on the 3DEXPERIENCE platform because it poses certain advantages. One is it offers a practical data storage method for customers who don't want to invest in IT infrastructure for storing large amounts of data. The next thing is scalable computing. A lot of folks, when they're running simulation, they need additional horsepower over and above their local computing resources. So you have access to cloud computing resources to 3DEXPERIENCE platform to speed up their analyses. But the biggest benefit is it essentially enables engineers across all spheres, the design, the data management, and in the simulation spheres, to be able to interact in a single environment. They're able to collaborate and share their product designs irrespective of their geography. So with almost no IT infrastructure, but just through storing and interacting with data on the 3DEXPERIENCE platform through the various apps, engineers are able to design products pretty efficiently. So that's why we will be focusing on the Simulia suite on the 3DEXPERIENCE platform for this session. And I'll be focusing on the structural analysis portion. So I'll go over some of the nuances of the FEA technology with this example I have here. So here is a boom that is supported by a bracket, and the major load-bearing element on this bracket are these knuckles. And my goal is to determine the structural strength of the knuckle based on the bearing loads that they undergo, and also to make some design changes to try and lightweight this knuckle and ensure that I'm able to maintain a factor of safety of over 2. Now, besides that, I'd like to demonstrate some of the fatigue analysis technology that we have access to. So I am testing this for multiple cycles. I'm testing this for not only static conditions, but also for survival. Now, as far as the solution goes, we have multiple solutions for structural analysis on the 3DEXPERIENCE platform, but just know that the commonality that these all share is they're all based on the Abacus solver. So each of these solutions gives you, additional level of capability as you, step through them. So for instance, the structural performance engineer gives you access to the standard implicit solver, while the mechanics engineer gives you access to both the explicit and the implicit solver. So all of these refer to the same technology, but just at different levels. Now, let me jump into the UI and kind of show you guys what the user interface for this looks like and how I went about setting up the analysis. So this is the local application, something we'd like to call the native app or the rich app. This is basically what we use to access the Abacus solver. And right now we are inside a simulation study that I've already set up. Now, how you interact with your model is through, 3 basic interface objects. One is this feature tree that gives you history of all the analyses, setup parameters. Then you have this little action bar that gives you access to all the buttons to set up the analysis. Then you have this little assistant panel that make sure that you're on track on what you're setting up, because sometimes these analyses can get slightly complex from a setup standpoint. So it'd be good to have this little assistant to remind you of what you have and what you've missed. Now, let's say you want to set up a new analysis, right? You can go ahead and just interact with this action bar, create a new analysis case, and essentially go about your way in setting up this finite element model. Now, the first few steps are essentially specifying a finite element container. So for that, you have buttons in the action bar to be able to specify an existing container or select a new or create a new one. Now, since I already have the mesh and the material properties assigned, I'm selecting an existing container. So that way I'm able to reuse an existing finite element model for different analysis for the same parts. So that's one common theme with the user interface in the 3DEXPERIENCE platform. It helps you essentially reuse existing data from an analysis and a design standpoint. Next, you can essentially set up multiple procedures from static to dynamic analysis. And when you talk about static analysis, you can basically specify step size if it becomes nonlinear. But since this is linear static, you really don't have to get into those details. Now you'll notice while I'm making all these changes and while I'm going through the setup, the assistant panel is updating with these little green check marks, indicating that these various stages have been set up already. So like I said, since I've reused the mesh from the study that I've already set up, the software has applied the that mesh to this model. But if I want to make a small change to the mesh, I can essentially interact with the feature tree, and I can go ahead and change the parameters here to remesh the model. But I wouldn't want to do that now because I'm quite satisfied with the mesh I have. Next, one thing I really like is some of the automated features from a structural analysis standpoint, because when you talk about multiple parts, you talk about contacts, and you want to be able to figure out an easy way to establish some of these contacts. And for that, we have these contact detection tools that enable you to automatically detect contact and apply it to the model. For instance, I'm going to use this contact search to find all the contacting surfaces and essentially tie them together for the analysis. And as I'm doing this, not only is my assistant panel updating, but my feature tree is also updating with all of these elements of of the study that I'm setting up. And the final thing I'll show you is just a load application, because I kind of like the little manipulators that I can use to change the orientation of the loads. So for instance, I want to apply a bearing load to the surface. I'm going to quickly hide the mesh. Hide. And I'm able to choose from choose the bearing load from this little action bar, and I'm also able to vary the position of this load by manipulating by essentially keying in what position I'd like the loading condition to be at. Now, so that should give you an idea about how this analysis is set up. I quickly want to show you one more thing before I jump into the results, which is, hey, how do you set up a fatigue case? Now, the benefit of this interface is that since you have all the data available from the structural analysis, you're able to use that to run the fatigue case. Typically, that's a disconnected process in other simulation tools. Now, to set up fatigue case based on the structural analysis results I've already produced, I can just go into this durability tab and set up a new fatigue case, and I'm able to and that gives me a set of commands to be able to set this up. Now, while setting up the fatigue case, there are some important parameters that I'll have to key in. The first thing I need to do is essentially tell the software, hey, am I running a nonlinear fatigue or a linear fatigue? Typically, this kind of superposition loading is used for linear fatigue. And then I can specify the structural analysis that I want to set up for the fatigue analysis, that I want to associate with the fatigue analysis. So here I have I have two of these structural analyses set up, so I'm going to set up the first one, and then I'm also able to specify the number of cycles of loading. So if I'm applying 1 million or 10 million cycles, I'm able to specify this repeat. And finally, I'm able to tell the software the loading ratio. So typically, most buttons that you'd find in a fatigue analysis in fatigue analysis tools to be able to set up this type of analysis. One last thing I'd like to show you again before I jump into the results is just the fatigue data. So we do have a database of materials that has some fatigue data based on the fatigue algorithm that you'd like to use. And that is all under the FE-Safe durability drop down in the material library. So we do use FE-Safe technology from Dassault Systemes to be able to run the fatigue analysis, and you have both stress-based and strain-based fatigue analysis tools. So you're either able to put in a stress strain curve, or you can put in some of these coefficients to be able to use the strain data to run your fatigue. Now I'll quickly jump into the results to demonstrate just the results from the basic structural analysis I've set up. So this is just a stress result from the static loading condition that I had, and the strength of this material is around 450 megapascals, and I'm barely crossing about 40 in all of these critical areas. So you have a factor of safety of 10. But the interesting thing is, if I actually switch to the durability case, I'm able to essentially predict damage, and I'm able to see, hey, what's the maximum amount of damage this component undergoes when I apply about 10 million cycles of this loading, which constitutes about 10% damage. Now, what this tells me is, 10%, I have 90% of the life of this component left, so I can actually make design changes because it's passed both static and fatigue testing. So what I went ahead and did was I was able to essentially change the model, and I was able to use the SOLIDWORKS connector to make a small change, and I was able to rerun the analysis to test the model. Now, the nice thing about this is not only was I able to do this, without having to set up the analysis from scratch, but also on the post-processing end, I'm able to turn on these comparison plots that's able to compare multiple results in the same interface. So you have design B on top and you have design A on the bottom, and I'm able to essentially make a comparison and predict, which of these designs, if the design change I implemented to design B is good. I'm going to switch to the damage plot so that I can tell, I can kind of show you the difference between the damage results. So while in the static condition, it did show that, hey, when I make this design change, there's a marginal increase in the stress experience by this component in this area. When I do apply, when I do take it to the fatigue side, it's telling me that, hey, your damage is increased from about 10% to about 40%. So there's only 60% of the life cycle of the component left. So if I apply 2 million cycles to this component, it would probably fail. So that's a very powerful result. Again, going back to predicting how long this component would last and if it will essentially be able to perform the functions that it was intended for. Now, let me jump back into the presentation and quickly summarize this little workflow. I was able to compare. I was able to run the fatigue static analysis with the interface, and I was able to make design changes just with the interface to be able to compare the static results for both versions of the design. I did find that although the design is acceptable, there are certain areas that have that experience a lot more stress than intended. And then finally, for the fatigue life, I was able to predict, hey, although the component showed that good performance for a single cycle, but for about a million cycles, the damage in this area was significant. So this probably is not an acceptable design. And I may need to go back to the drawing board and maybe increase that fillet size to strengthen the design a little. And that concludes my portion. I'm going to pass it off to Ramesh to demonstrate the CFD technology. Ramesh, are you able to share your screen?
Yeah. So can you hear me okay?
Yep, loud and clear.
Okay. All right, so just a quick check again. So you should be able to see my PowerPoint.
Yep, I see it.
Okay. All right. Thanks, Arun. That is a great overview of the structures roles. So I'm actually going to talk about SOLIDWORKS, not SOLIDWORKS, sorry, fluid mechanics engineer, which is a fluid dynamics engineer, which is our CFD tool on the 3DEXPERIENCE platform. Now, so I'm going to illustrate a quick example a little bit later on, but first I want to actually start off with introducing you to some of the fluid solutions actually that's part of the Simulia brand at Dassault Systems. So we're going to talk about an example later on with that's solved in fluid dynamics engineer, and how this is actually both CAD, PLM embedded, as well as there's so much of these in terms of physics. There's a broad coverage as well with fluid dynamics engineer. We have a body fitted mesh, and we have several types of advanced turbulence models as well with in fluid dynamics engineer. So we'll talk about this a little bit more in great detail later on. But we're all, as part of the fluids portfolio, we also have plastics injection engineer, which is nothing but your SOLIDWORKS plastics tool. If you think about it, some of you might have ownership of that tool today. But it's basically if you design plastic parts, and if those plastic parts are manufactured through injection molding process, this is a great tool on the cloud, on the 3DEXPERIENCE platform to take advantage of as well. And then we have on the very advanced side of the CFD analysis, we have tools like XFlow, which is based on a little bit different technology. Like, for example, fluid dynamics engineer is based on the RANS method, the traditional RANS method, whereas XFlow, for example, is based on the lattice Boltzmann method. And it's really a tool that is for very high transient, high frequency applications, any kind of multi-phase or moving geometries, fluid structure interactions. This is a great tool that can actually help you out if you have those kind of situations, or if you're designing products that actually form in that realm of safety analysis. We also have another tool called Power Flow, which is based on the same lattice Boltzmann technology, but it's also, again, for highly transient industrial applications. So I would think about this as a very niche tool that actually solves very specific engineering challenges in a lot of the key industries, such as aerodynamics, aeroacoustics, aerothermal applications, and so on. Okay. So I'm going to talk a little bit about the technology behind fluid dynamics engineer on the 3DEXPERIENCE platform. So there is a broad physics coverage. I'm not going to read each of these bullet points here, but you can see that it's pretty when it comes to physics coverage, there's a lot of things that this tool actually can bring as a value add-on to the table. Now, in terms of turbulence modeling, that's another key technology I would like to talk about. So like I said earlier, it's based on the RANS turbulence model methodology. And there are several types of turbulence models like the Spalad-Almaraz, realizable K epsilon, and SST K omega, which is a combination of the K epsilon and the K omega turbulence models. And combined with this, and one of the big technologies that we have is what is called as near wall modeling using a hybrid wall function approach. So this is really depending upon the coarseness of the mesh in the boundary layer, the program automatically switches between different algorithms automatically. The other technology is the meshing process. So we use a body fitted mesh, and which is actually, if you think about it, a hex dominant mesh is what is mostly used for actually meshing the fluid domains. But again, that's the dominant technology that we use, but there are other types of meshing techniques also available for you to use if you have a need to use, such as, for example, a sweep mesh, or maybe a hex dominant mesh, or maybe it's just a tetrahedral mesh or a surface mesh, whatever the case might be. You can mesh your fluid regions with different mesh options. Okay. And then, on the scalability side, I think that's one of the big value add-ons of Fluid Dynamics Engineer, because it's actually on the 3DEXPERIENCE platform. You get access to solver scalability, being able to actually scale your simulations using multiple cores. And so out of the box, depending upon the package, like for example, Fluid Dynamics Engineer, out of the box, it allows you to use 16 cores. Okay, the structures role that structures package that Arun talked about allows you to use 8 cores out of the box. Okay, so and then for any additional core, you can up to 144 cores, I believe, on the local machine as well as on the cloud. The program allows you to use that many cores, but for anything beyond the out of the box allowable cores, you have to actually purchase what is called as tokens or credits to use the additional cores if you want to. Okay. Now, so being able to do this, the scalability of your physics problems that you're solving, right? So it's a linear scaling. With every additional code you can run, you're running the process, or the solve is actually running a lot more faster. And then with respect to cloud, right? Again, it's the same as in terms of out of the box solution. You can, if you have access to Fluid Dynamics Engineer, that means you can actually utilize cloud architecture or cloud resources to up to 16 cores. And if you want to use anything beyond 16 cores, you have to buy those additional tokens or credits to utilize, more cores on the cloud as well. But one of the key benefits of the cloud is it's got infinite, almost like a lot of memory, I would say. Okay, so really for solving these type of large scale problems, complex problems, especially when you're talking about, Arun talked about nonlinear analysis, some of the problems can actually take a lot of time, but using cloud resources, now those problems can be actually solved in a matter of seconds, in a matter of minutes. So if this initiative, in terms of reduce hardware infrastructure or reduce IT overhead costs that you and your department or the entire company might be looking to do in the short-term, long-term future, this could be a good fit for your company when it comes to simulation needs. All right, so let's talk about a quick example. So since we are on the topic of industrial equipment industry today, I thought, okay, maybe this is, we can actually look at how For example, using this multi-cyclone separator, we can illustrate the value and how the fluid dynamics engineer, the CFD tool, actually works. So in this example, the scenario is pretty straightforward. You have air coming in from the left-hand side as shown. Air is coming out on the right-hand side as shown. What is critical to know at this point is there is a fan blower. Okay, so let's say, for example, we want to understand what fan we should be using for this entire design. So the left-hand side picture is the actual design, and then we're trying to figure out which fan we should be using depending upon the flow requirement in the system. Okay, so let's say we have some standard fans which are off the shelf that we get ready to use for this design. So it could be a 601 fan, it could be a HP or a HP NW type of configuration. So whatever the case might be, let's say we have some standard fans that we can take advantage of to get the job done. So in order to understand what the fan requirements are, we'll use Fluid Dynamics Engineer to get us close to our goal of figuring out what is the fan which will actually get the right pressure drop and the right flow rate through the system. Okay. So what I want to do is start off with some key highlights. So I'm going to talk a little bit about the assistant, the body fitted mesh, the compute options, and then we'll take a look at some key results on the baseline design. So I'm going to go ahead and switch to my simulation fluid dynamics engineer role on the 3DEXPERIENCE platform. So I have a result already run, but that's not what I want to start off with. So let's go ahead and try to look at, for example, a model that does not have any simulation setup. So I'm just going to go ahead so I have several configurations I set up for the purpose of today's presentation. So I'm just going to start off with this particular analysis case. And what I would like to highlight is using the assistant. So the assistant is something that's also available on the CFD tool on the 3DEXPERIENCE platform. So Arun gave you a sneak preview of how it works on the structure side. It's exactly the same workflow here. There's nothing different here. So all I'm doing here is basically telling the program, okay, let me just walk through a step-by-step process. I'm actually going to go ahead and go through a couple of basic steps. I'm not going to go through the entire setup of this problem, but hopefully you can see what I'm doing here. So let's call this as a baseline iteration. So right at the bat, the program is actually going to ask me, hey, you have this big assembly. What components do you want to analyze in your CFD analysis? So that's what I'm looking at here. So I'm just going to grab everything I can, but then I'm just going to go ahead and click OK. And so then what I'm going to do is I'm just going to go back and say, all right, let's go ahead and define the physics of this problem. So I'm just going to go ahead and define a fluid domain. And basically, these are the very key, the first few steps on the pre-processing side that you would probably have to deal with to set up the problem. So let's see, for example, I'm just going to say, let's add all the parts. And I'm just going to window select everything. So this assembly is about 80 meters long. It has about 516 components in it. So I'm just going to window select everything, done. Okay, very simple step. And then I'm just going to go ahead and define where my fluid exists. So I'm just going to zoom in, and I'm just going to go ahead and grab the inside surface of this tube. So that basically is telling the program, hey, that's where my fluid is going to exist. And so in Fluid Dynamics Engineer, we call that as the region. Okay. So it's just terminology that we use internally. But basically, it's a simple geometry selection. And then I move on to the next step. The next step is really telling the program where are the openings, right? So what is really nice about this Fluid Dynamics Engineer is that, for example, I can just grab the edge over here, and the program knows it puts up a fictitious surface, a virtual surface, and let's call this as inlet. Okay. Click OK, and I'm done. Let's add another opening. Where do you think the other opening is? Well, it's it's on the right side here, the square duct opening. So I'm just going to grab all the edges over here. All right. And let's grab this edge. And so I grab all the 4 edges, and let's call this as outlet. And that step is basically done. Okay. So it's a very easy process. I just showed you a few steps. So next is to go ahead and define my fluid section, which is nothing but what type of fluid do I want to use in my analysis. So I'm just going to grab my fluid region here, and then I'm going to go ahead and apply select a fluid of interest. Just like what Arun was showing you earlier, there is a material palette, which is a database of different types of materials, solids, gases, liquids, all built in. So I'm just going to go ahead and say, let's pick a material that's in session, means I don't have to go through the laundry list and figure out then select air, but I can quickly do a filter. Like in session means this material has already been applied or being used somewhere else in my analysis. So when I have a scenario like that, I can quickly use this in session. So let's pick air. All that I care about is verify some properties of the simulation, such as viscosity and density. That looks pretty good to me. Click OK. I am done. So it's a very simple process. Okay. And the assistant is a great place to get started, right? It's a step-by-step process, especially if I'm new to the tool. You're new to the tool. You're trying to use this on day one. Use the assistant. It walks us through a step-by-step process and telling us exactly how to set up the problem, how to measure it, how to post-process the results, and so on. Okay. The next thing I want to talk about here is what is called as a little bit of the meshing process. Okay. So let's switch to another setup I have. So what I want to show you or illustrate here is the meshing process. It's super simple. This is in Fluid Dynamics Engineer. There are several options to help you mesh the geometry. Well, if for fluid regions, typically the hex dominant mesh is used. But what I want to show and illustrate here is, for example, how easy it is to create boundary layers. Okay, so I'm going to go to the mesh manager, and I've used a hex dominant mesh. So for example, I can initialize the mesh based on the geometry. So that's a very easy step. But what I want you to notice here is I can just simply check this box called add boundary layers and specify the first layer thickness, number of layers. Great. Maybe for this problem, it may not be absolutely important to add boundary layers, right? Which is between your fluid and solid regions, but it could be, but what if the surfaces are rough, right? The pipe surfaces are rough. What if you want to capture, maybe there is a super narrow region in your model that you want to capture the fluid effect, the flow effect as accurately as possible. So all of that will require you to actually add boundary layers in your mesh, right? So if you're solving, let's say, some sort of an aerodynamic problem, you need a boundary layer. But what I'm illustrating here is how easy it is to actually add boundary layers to your mesh without actually going into the nuts and bolts of the meshing process. Okay, so we just check this box and specify a couple of inputs and let the program do all the hard work behind the scenes. Now, what I want to show you on this mesh, though, is let's go ahead and take a quick cut section. Oops, sorry, I think it's so I'm going to cut through the model, and let's just go ahead and zoom in. Oh, let's see. So let's hide the geometry. Okay, so I have a cut mesh, but so let me zoom in so you can see that boundary layer effect. So it's super easy. Hopefully you can see the boundary layers. Arun, can you confirm if I'm zooming in too fast? It might be a little bit choppy if I kind of try to zoom in, zoom out.
It's perfect, yeah.
Okay, so you can see that these boundary layers are actually a very simple thing to do when fluid dynamics engineer. Okay, so especially when it comes to the meshing process, you want to capture the pressure gradients more accurately in a pipe problem like this. Doesn't matter, if you want to add boundary layers, it's a simple step. Just keep that in mind. So the other one is, let's go back and let's switch back to the other analysis case I have. So that's actually called the flow analysis case one. So I have this model. I actually have all the setup done. So I have, for example, the physics defined as a steady state analysis. I have some boundary conditions. So I'm basically saying, look, here's my flow rate through the system. So that's, let's say, about 20,000 CFM of air is entering through this opening here. And then the outside, so you can see that I don't have the fan portion of the assembly yet, right? Because I'm trying to understand what fan should I use eventually to get the job done. So initially I perform a series of experiments. So for that experiments, I'm just saying, okay, let's test different flow rate through the system. And then the outlet pressure is just, 0 pascals. The gauge pressure is 0, which means it's just ambient conditions. So all I want to know is for a flow rate, a certain flow rate, in this case, 20,000 CFM, what is the pressure drop across the system? As simple as that. Then I want to simulate that for multiple CFMs, like maybe I want to test 30,000 CFM, 40,000, 50,000, 60,000. So that way I can actually get some enough data points to basically see, what fan can actually get the job done. All right. Now, before I do that, you can do a lot of things. Once you run the analysis, you can look at some key results. So for example, you can look at maybe pressure, velocity, streamlines. So you can look at XY plots. So there's a lot of different types of results you can look at right off the bat. Okay. All right, so let's just give it a few seconds for this to load up. And while that is happening, okay, it looks like it actually loaded up the results. So let's talk a little bit about the results. So there's several types of visual feedback that you get from the program, right? So visual feedback is really critical. You can actually look at the flow trajectory. Right now, we're looking at the gauge pressure representation, and we are actually superimposing the streamlines on top of that. You can actually go ahead and play an animation of the streamlines. Whatever the case might be, just understand how the flow is traversing through the entire system from the left to the right. So it's three-dimensional, so it gives us a good idea of what the flow is doing in the system and what the pressure looks like in the system. Okay. You can also go ahead and look at, for example, let's just go and look at some XY plots, right? So visual plots are good. Great feedback. We can make some good design decisions right off the bat. But we always need, as engineers, as experts, as analysts, we always want to back up those visual decisions with engineering data. So so here, for example, I want to know, let's say, for example, I want to look at the flow rate at the inlet. So that's about 20,000 CFM. Well, that's an input, right? Obviously, it has to be 20,000 CFM. Am I getting 20,000 CFM at the outlet? So it's a negative. Negative means the flow is coming out of the system. So there you go. So that looks pretty good to me, right? I can also look at, for example, the pressure in the system. Let's close this. All right, so I can see, I can superimpose, I can have multiple XY plots. So here I'm looking at flow rates, pressures at both the inlet as well as the outlet. So I can get a variety of different information right off the bat using this XY plot. All right, so let's go back into the PowerPoint real quick. So this baseline design, we reviewed the assistant, the body fitted mesh. We talked a little bit about the local cloud compute in one of the earlier slides. And we also looked at some key results. So what we want to do is move on to the next step, which is, design of experiments. So earlier I said, okay, look, if we have actually a flow rate in the system, we get a certain pressure drop. We saw that, in the previous case. But what if I want to actually change, different flow rates? One option is to change the flow rate manually, see where the pressure drop is, then change the flow rate and keep on doing that. But what I can do is I can actually now take advantage of another tool on the platform, 3DEXPERIENCE platform called as parametric design study. So here, what you're looking at the video is just several parameters like sensors or pressure drops or inlet pressure, outlet pressure, exit velocity. So what I can do is I can actually now automate this process of testing multiple iterations using the parametric design study. So I have, for example, the CFM. I want to change it from 20,000 to 60,000 CFM in steps of 10,000. And I want to monitor the exit velocity, inlet pressure, outlet pressure, and so on. So this is a great way for us to, okay, before I say that, you can also add different design constraints as well as an objective. In this case, the objective is the pressure drop. I want to minimize the pressure drop in the system. So once we run this parametric design study, this is the interface. Obviously, it's completed at this point, but it's the same interface that you get access to. It's super interactive while the analysis is running. So I can check what design points are best or what design points are feasible or not feasible. And so I can gather all of that information I'm after. In this case, for different CFMs, I want to get the pressure drops. I can also investigate using this tool a little bit more in terms of some of these contour plots, the graphs, the XY plots. So whatever the case might be, I'm just getting more and more data. But the good news is all that is completely automated. Okay. So once I'm actually done with this, then I can gather all of that data, right? So this table at the bottom here summarizes all the data I'm getting from this particular design from Fluid Dynamics Engineer, like what's the flow rate from 20,000 to 60,000, what's the exit velocity, what's the pressure drop. And then I can take that information and kind of, marry that with the fan curve data I have, right? So this is HP 601, HP 601 NW. And you can very well see that, at right about 40,000 CFM, I might be able to actually use this HP 601 fan. And so that's an easy decision for me to make right now because I have done all the experiments and now I'm actually getting, I can take the next steps in my design, which is to go ahead and complete my setup. Okay, so let's just go back and I want to actually go ahead and show you the completed setup. So the workflow doesn't change, right? All we're going to do is now we figured out what fan is the best fan to use. And so I'm just going to go ahead and include that fan in my setup. So I put the last leg of this geometry into the analysis. Everything else remains the same. And all I'm doing here is moving the pressure outlet right up to the top and then putting a fan condition. So let's take a look at the fan. So it's a 3D fan, which is nothing but it's an internal fan. And all we do here is input the flow rate versus the pressure drop. And we can even enable swirl velocity. So we can see, as the fan is sucking in the air from the left side, you can actually get access to, and you want to see that swirl effect as well in the fan. Okay. So this is basically the workflow for this particular design, going, taking step by step, going from a baseline iteration, then figuring out what's the right fan to use, and then finally concluding, concluding, which is the best fan, which will get the job done, and then including that fan in the process, and then looking at some key results. So here is what the pressure plot looks like. Sorry, not this one. So let's just switch to the results with the fan. So it might take a few seconds. And there you go. So now you can see the difference, right? So all I have done is included the last leg of the geometry, the fan blower geometry, and used a fan boundary condition. Everything else, the rest of the physics is exactly the same, right? So this actually completes my setup process, my analysis process. I do have, another example to show, but I know we are at maybe running short of time. So I'm going to hand it over to back to Arun, and then maybe if we have time later on, I want to revisit. I want to show you another example, but that illustrates, how this parametric design study works in conjunction with your SolidWorks design, how you can drive your SolidWorks designs on your desktop using parametric design study on the 3DEXPERIENCE platform. So we'll come back to that if we have a little bit of time, but right now I'm going to hand it back to Arun.
Awesome. That was an awesome overview about the CFD technology on the platform, Ramesh. Especially the parametric study tool. I think it's going to make a lot of our workflows pretty handy.
Yep, absolutely.
And that parametric workflow is on the structural side as well, right?
Correct.
Awesome. Awesome. Thank you. And for the rest of the presentation, I'll just spend another 5-10 minutes just talking about how this technology has been adopted by existing industries. And I'll wrap it up with all the portfolios that you've seen today and what you can expect from the 3DEXPERIENCE platform in terms of simulation moving forward. I'll start out with this LNT case. LNT essentially uses the Abacus technology to execute these rollover protective structures tests. The importance of these tests is they ensure operator safety, and they also required to pass the ISO OECD standards. The biggest challenge behind executing these tests is that they're very complex. You're trying to simulate a very a post-buckling event. It involves damage, which involves material fracture and separation, and you really need a sophisticated analysis tool to be able to perform all of these, incorporate all of these complexities, and perform a structural analysis. This is where the explicit solver from Abacus was a perfect case to be able to execute this dynamic scenario, incorporating the post-buckling, the metal plasticity, the multiple points of contacts that's set up during the analysis, as well as determining the buckling force during the ROPS test. Another example is Shaflow. I'm pretty sure you've heard of this company. They're a very popular bearing manufacturer, and they essentially used the Abacus solver to be able to test what kind of bearing cages they can essentially implement for their roller bearings. So they want to look at the strength of their existing bearing cages and come up with creative designs. Now the biggest challenge behind executing this is they wanted to test this while they needed to test this while this bearing was in motion. So this is a combination of a motion analysis where you're simulating the motion between the inner and the outer rings, and also studying the change in stress and contact distribution between the rolling elements as well as the cage. Again, another thing that was quite easily simulated with the Abacus explicit solver. They were able to simulate the motion as well as utilize the nonlinear dynamic or the explicit analysis capabilities to be able to execute these problems. In that vein, they were not only able to run the analysis, but they were able to make strain measurements, and they were able to match that with FEA results as illustrated by this little screenshot here. Now, what you're seeing here is essentially the Abacus explicit technology, but implemented in the 3DEXPERIENCE platform, but they basically use the legacy portfolio to be able to simulate that. But this is just an example of what that analysis would look like in action on the 3DEXPERIENCE platform. Finally, the more recent case of the implementation of the Simulia technology on 3DEXPERIENCE platform comes from Canada, from a company called InFocus Energy Services. They make machine tools for a plethora of applications. This one particularly, they were trying to fix a problem with one of their drilling equipment. So their drilling motors essentially incorporated traditional bearing system that failed both in static and fatigue cases. They undergo a lot of bending loads, and they invariably ended up failing. So they couldn't rely on traditional bearings, so they had to design their own. And because it's such a nonlinear case, it involved multiple points of contact. It involved the rolling elements as well as the races, as illustrated by the previous slide. It required something as sophisticated as Abacus to solve it, and they were able to use that to come up with creative designs and also create materials to be able to execute this application to ensure it didn't fail due to the bending stresses that this little motor underwent, or this bearing underwent. Finally, some other examples of how this technology is implemented in the industrial equipment sector is primarily in shock and vibe. So here you see an overhead rail system. The goal of this analysis was to determine, hey, if this rail system came to a sudden stop based on the center of gravity of all the components that's on the rail system, how will this behave and what is the stress distribution on the rail system? So that is so that is something that incorporated both the shock and wipe test and also stress determination that changed in time. Now, a final, I guess this would be the probably final slide of the types of static structural tests that are executed with industrial equipment, which is a crush test, a roof crush test. Here again, you're ensuring operator safety, and the biggest challenge behind this test is because you're simulating it comes from being able to simulate a short duration, highly dynamic event. Another area where the explicit solver from Abacus essentially shines at. Now, not only were we able to simulate this test and the dynamics involved, but we were also able to simulate the permanent deformation that a couple of these components can undergo during this process. Again, the key thing is our ability to simulate excessive deformations, incorporate nonlinear material properties such as post-yield deformation of metals, rubbers, and plastics, and also being able to take advantage of the automated generalized contact capability to be able to simulate the contact between different components with minimal user intervention. That's really the claim to fame and why the industrial equipment sector essentially adopts our structural solutions from Abacus. Now, as far as the 3D Experience platform goes, there are multiple tiers of structural solutions that you're able to adopt. The design and the engineer tier gives you access to the Abacus solver to be able to solve linear statics and certain vibration problems. But when you get into the performance engineer and the mechanics engineer tier, that's where you get access to the nonlinear, static, and dynamic capabilities, where you're able to push, the level of your analysis beyond, an existing solution that you might have. Again, the takeaway is that not only are we able to utilize the Abacus technology to be able to run these static and dynamic analysis tests, but we also have the fatigue analysis capabilities from FE Safe that we are able to utilize to run life cycle assessments for high cycle fatigue and low cycle fatigue, both linear cases and non-linear cases, to ensure to essentially study product performance over its entire life cycle. There are also features like the material calibration app that you can essentially utilize to be able to calibrate your experimental data into material models that can be utilized in the software. So there's a lot of little modules like that makes your simulation process really simple. And while Ramesh demonstrated the parametric optimization on the CFD side, this has been implemented on the structural analysis side as well. So here you see a sheet metal assembly that has some static testing and some modal testing. And based on the static and modal testing, you're able to define them as constraints and also go through a set of parameters using the parametric design study app to come up with an optimum design to conform to your constraints. So here, this is a nice little eye candy. This is essentially going through all the possible designs that the software is about to test. And then this slide, it's all the designs that the software deemed feasible and it has tested with the results. So you have this nice little chart that essentially tells you, hey, what is the modal frequency versus the design type or the design iteration number. Everything below this red line indicates that it's an unacceptable design. Everything above the red line indicates that it is an acceptable design. So in that way, you're able to identify an optimum from hundreds or hundreds of iterations of your design as you change its parameters. Finally, that wraps up the structure side. And Ramesh went into detail about the fluid side, so I'm going to jump over this really quick. You saw the parametric optimization from Ramesh on the cyclone separator on the CFD model that he presented, but here is again a little parametric optimization eye candy where you're able to speed past all the iterations of the design that the tool went through and also the results produced as a result of those iterations. So you're able to visually validate what is the most feasible design, and you're able to extract that design and save out that geometry. One thing that isn't very often talked about, but we hear about a lot, is the electromagnetic solutions. So now we have access to the CST Studio Suite from Dassault Systemes, both on the 3D Experience platform and off of it, to be able to tackle both high frequency and low frequency applications. Typical examples of low frequency applications are motors, magnets, and sensors, and typical examples of high frequency applications are antennas and any kind of signal generation and reception device. So we're able to figure out magnetic fields, look at magnetic saturation, look at thermal effects of electromagnetics, and so on and so forth. And with that, I'll conclude this presentation. Again, thank you so much for joining us, everyone. If you'd like to learn more about this technology, please feel free to contact us. And also, we have a YouTube channel dedicated to our 3D experience, to getting good and getting accustomed to the 3D experience platform that you can check out to see this technology in action. If you'd like to take a look at more industry examples from Simulia, you can check out the ifv.3ds.com, where you have a plethora of examples from different industries. And finally, if you'd like to learn more about the technology that Go Engineer is able to service, please check out our website. Other than that, again, thank you for sticking around. And if you have any questions, please feel free to put them in the chat or in the question and answers box, and we'll address your questions for the rest of the presentation.